Okay, so we're now coming to problem 2. So consider a spherical vacuum capacitor consists of inner and outer thin conducting spherical shells with charge plus Q on the inner shell and a radius A, and a charge minus Q on the outer shell of radius B. You may neglect the thickness of each shell. Express all answers in terms of R, epsilon naught, Q, A, and B as necessary. Sketch for the above capacitor configuration the electrical field for the radial region between A and B, along with a clear choice of coordinate system, a Gaussian system needed to determine the electrical field between A and B. Alright, so problem 2. So now let's sketch here this spherical capacitor. So inner radius is A, outer radius is B. So here is A, this is B, A, B. And then let's choose here a Gaussian surface in between. Since we have spherical symmetry, we use a sphere as a Gaussian surface, so we just sketch here in red. So that's the Gaussian surface. And then denote this here as generally radius R. Okay, and then the charge is here plus Q on the inside, plus Q on the outside is minus Q. So therefore the electrical field is then radially outwards. So I draw here a couple of examples for field lines going from the positive charge to the negative charge. Okay, I think it should be clear. So that's the electrical field. And then we have here normal vectors on that sphere. So this is N here, and this is electric field vector. Okay. So now on the inside is the electrical field is 0. There's no charge enclosed. We have then an electrical field between A and B, and then outside of that. So let's see. Sketch the for the above capacitor, configure the electrical field, and make a clear coordinate system. So we're using spherical coordinates, the radial unit vector pointing radially outward. In a Gaussian system is the Gaussian surface. So that's the sphere. Okay, so that was part A already. Then in part B, determine an expression for the magnitude of the electrical field in each of the regions. So, well, E dA equals to 1 over epsilon naught times the enclosed charge. So therefore now, for the first radial region R less than A, we now have, since the enclosed charge is 0 and the actual surface is non-zero, so therefore the electrical field inside is 0. Secondly, between A and B, so what do we have now? The enclosed charge is now plus Q, so therefore we have now the left-hand side, EdA, E times dA at every point are parallel vectors. You can write a vector E times vector dA, so vector E times vector dA is therefore E dA, but for every point on that surface E is a constant, so you can take this out of the integral, so you have that E dA, and this is here nothing else than E times that surface of that sphere, radius r, 4 pi r squared. So and now on the right hand side, that equals to 1 over epsilon naught times the enclosed charge. So this would be plus q. All right, so now we can solve this for the electrical field. So this would be then E equals to 1 over 4 pi epsilon naught times capital Q times r hat. All right. So that's the result for part 2 here. For the middle section, the electrical field inside is 0. There's no explicit charge inside. And then the third region, r larger than b. So for r larger than b, well, here the enclosed charge equals to plus q plus minus q, so it's actually 0. So therefore the same argument, the actual surface is non-zero, therefore the electrical field has to be 0. Alright, so this is already done. And as you can see, the electrical field is identical to a point charge inside, as if that point charge, oh, and I of course forgot something very important here, dividing this here by 1 over r squared. Identical to a point charge sitting here at the center of charge plus q. So now let's go on right away to part C. So V final minus V initial equals to minus the electrical field E dr. So V B minus VA equals to minus the integral from RA to RB E dr. So E is given up here, dr equals to dr r hat. So this is then something very simple, minus, this would be 1 over 4 pi epsilon naught times the charge q, epsilon naught. Then we would have here an integral 1 over r, 1 over r between rb and ra, but there is a plus sign here. So therefore we end up to be q divided by 4 pi epsilon naught times 1 over rb minus 1 over ra. Okay, so that's the end result. So vb minus va equals to q over q over 4 pi epsilon naught 1 over rb minus 1 over ra. Yeah. So now you can write this in a little bit more an elegant form. Let's label this here as 1, 2 here. You can also write this as delta V equals to VB minus VA equals to Q over 4 pi epsilon naught. This would be then RA minus RB divided by RA, RB. But since RB is larger than RA, this would be negative, so the absolute value of delta V when recording the capacitance is therefore Q divided by 4 pi epsilon naught RB minus RA divided by the product RA RB. Alright, so that was this, and then we have how much energy stored, determine the capacitance, so part D, determine the capacitance. The rest is now completely really easy. Capacitance, let's see, simply plugging this in here, C equals to Q divided by the absolute value of delta V. So you divide out Q, so then we have here simply 4 pi epsilon naught. This would be then RA, RB divided by RB minus RA. Okay, so that's this. Then E, the energy stored in the capacitor, this would be U equals to a half Q times absolute value of delta V equals to, so you multiply this expression by Q over 2, so then we get here Q squared divided by 8 pi epsilon naught RB minus RA divided by RA times RB. So, and last but not least, part F. Now consider the case that the dimension of the outer shell is doubled from B to 2B. What is the change in the stored energy? So we're basically going now from, we're evaluating delta U equals to U of 2B minus U of B. So instead of him having here RB, we have 2RB. So that would be then equals to so let's see. So we would have here Q squared divided by 8 pi epsilon naught. Then we have here 2RB minus RA divided by RA times 2RB minus Q squared divided by 8 pi epsilon naught. And then here we have RB minus RA divided by RA times RB. So now we can simplify this a little bit. All right. So we can take Q square divided by 8 pi epsilon naught out, Q square 8 pi epsilon naught, Q square epsilon naught. And then we have here 2RB minus RA divided by 2RA RB minus RB minus RA divided by RA RB. So now, how can we simplify this further? Q squared divided by 8 pi epsilon naught. This is then what? Well, we take here 2 RA RB. This is then 2 RB minus RA minus, and multiply this by 2. Then we have minus 2 RB. Minus plus 2 RA. So then this goes out, and then you have here plus RA, plus 2 RA, minus 2 RA. So then we have here Q squared divided by 16 pi epsilon naught, 16, 8 pi epsilon, so 2 times 8 pi epsilon, 16 pi epsilon naught, and then you have here 2RA minus RA is RA, divided by RA over RB, so this cancels out, so then we have here times 1 over RB. So the end result is delta U equals to Q squared divided by 16 pi epsilon naught times 1 over RB. So that was this.